Hi, this is Mrs. Often, and this is More About Functions, a continuation of the previous lesson about functions. In this lesson, you will learn and be able to identify intercepts of a function either from a graph or algebraically, both x and y intercepts, identify intervals over which a function is increasing or decreasing, identify end behavior of a function, and identify relative maxima and relative minima of a function. To begin with, we'll look at intercepts of a function from a graph. Now, we could be looking at the x-intercepts or zeros of a function, or we could be looking at the y-intercepts of a function. Given the graph here, we can estimate the x-intercepts or zeros to be located at approximately x equals -4, at approximately x equals -2, and at approximately x equals 2. And so I'll write those as coordinate points, approximately -4, 0, -2, 0, and 2, 0. We also have a y-intercept located at 0, 1. So that's how we would use the graph to identify the intercepts of a function. We can also determine this if we are given the function equation through the use of factoring or the quadratic or cubic formulas. Let's look at this example of a cubic function. I'll set it equal to 0 to determine my x-intercepts or zeros of the function. So I'll factor this, and this will factor as x squared minus 1 times x plus 3, or x plus 1 times x minus 1 times x plus 3. This yields x-intercepts at -1, at +1, and at -3. So those would be the zeros, the real zeros of this function. Additionally, when we substitute 0 in for x, we can determine that the y-intercept of this function would be at 0, -3. We can do this with this cubic or this quartic function as well. It's conveniently written in quadratic form, so that helps us out. So factoring this, we get x squared minus 1 times x squared minus 1. Now factoring this, we'll get x plus 1 times x minus 1 times x plus 1 times x minus 1, and with some rearranging, we see x plus 1 squared and x minus 1 squared. This yields x-intercepts at -1 on the x-axis and at +1 on the x-axis. Each of these would have a multiplicity of 2 because they would occur twice. In addition, substituting 0 into the function formula yields a y-intercept of 0, 1. Functions can increase or decrease over open intervals, or they can be constant on an open interval. Please note that these are on open intervals, which are written with the round parentheses. So a function is increasing on an open interval if for any x value in the interval, x1, that the value of the function f of x1 is less than f of x2 when x1 is less than x2. So that's increasing. As the x's increase, the y values or the function outputs increase. Decreasing on an interval if over the interval the x values increase but the output values decrease, then it is decreasing on an interval. And the function is constant if the values of f of x1 and f of x2 are equal for any x1 and x2 in the interval. Let's look at how we would write these intervals. Okay, so I'm given two graphs here. One is a quadratic, and I'll just trace that so we can see. And I'll also mark the origin here. And we have this cubic function, which I'll also sketch so we can see a little bit better and mark the interval. When we're talking about intervals of increase and decrease, we are talking about x values, not y values. So we want to have what x values or what input values are those increasing or decreasing intervals. So in our first one, we can see that it's increasing over here to the right of 2 on the x-axis. So my interval of increase would be from 2 to infinity. My interval of decrease would be from negative infinity all the way up to 2. From my second graph, I can see that there's one interval where it's increasing. It's right here in between -1 and +1. And my intervals of decrease would be from negative infinity to -1 and from 1 to positive infinity. Please keep in mind that unlike domain and range, where you may use round parentheses or square brackets, for interval notation on increasing and decreasing intervals, we are only talking about open intervals, thus you should always be using the round parentheses. We also want to discuss end behavior of functions. This describes what happens as x moves towards positive infinity and towards negative infinity. So looking at this function here, which is a cubic function, we can see that as x goes to positive infinity, this graph would be continuing on. It would be going negatively. So f of x tends towards negative infinity. On the other side, as x goes towards negative infinity, the y values or f of x values tend towards positive infinity. Those of you who are going on to take calculus, please note that this will look a little bit different when you start discussing global limits, but this notation is just fine for us right now. We also could have that a function is a constant function or replicates a constant function for part of its domain or range. And in that case, we may have a case like this one. So here's a function that is just going to kind of do some stuff over here, and then it's going to switch and it's going to head along this line that is similar to y equals +1. So in this case, as x goes to negative infinity, over on the left-hand side of the graph, f of x also goes to negative infinity. The arrow is pointing down. So there's my end behavior on one side. On the other hand, as x goes to positive infinity, this graph is remaining as a horizontal line. So f of x is going to go towards 1. It does not change. So that can happen sometimes. Most times with our polynomial, radical, rational functions, we will see that the end behavior is either infinity or negative infinity. But do keep in mind that it could approach a constant. The last thing that we're going to talk about is maxima and minima of functions. So maxima is simply the plural of maximum, and minima, the plural of minimum. So we're looking at the maximum value of a function and the minimum value of a function and where those occur. Looking at this function, I can see that there are maximum points here and here, and there are local minima here, here, and here. Additionally, this function has a global maximum here and a global minimum here. Not all functions have global maxima or global minima, and some do not even have relative or local maxima and minima. We can estimate these values through use of coordinate points. So my relative or local maxima is occurring at -3 and approximately 4.5. And another local maxima is occurring at 1, 3. Our relative minimum points are occurring down here in the negative part of the coordinate plane, quadrants 3 and 4. And one is occurring at -4, that's approximately -1.5. Another at what looks to be about -1.25 and maybe -2.5. And lastly, here at 3, -3.25. I hope this video has been a helpful introduction to more features of functions. Thanks and have a great day.